Okay, so we're recording, and let me be sure, where is it? Here it is. Sitting, let's see, audio is usually the problem. Let's turn that up. Okay, now we're good. Slideshow going. This is our last chapter, acids and bases.
Drop the bases.
Huh?
Drop the bases.
You don't like bases?
Drop the base.
Oh, okay. All right.
Wow.
So these are just topics that we're going to cover, so we're not going to spend the time on that. The first coherent theory of acids and bases, actually what they are, was proposed by Arrhenius. He was a Swede. During this time, there was a lot of chemistry activity in Scandinavia, Sweden and Denmark. They were prominent worldwide. But Arrhenius proposed that an acid is anything that when you put it in aqueous solution, it produces protons. Right? So this is nitric acid, so when you put it in solution, it dissociates into hydrogen ions, which is a proton, and nitrate ions. Okay? Bases, he said, were any compounds that produced hydroxyls from their structures. So sodium hydroxide would be a candidate that would dissociate into sodium and hydroxyl ions. And that works for most bases. You know. But they soon encountered bases that produced hydroxyls, but their structures didn't have hydroxides in them. So they had to come up with a new theory. Oh, okay, your book goes into, all right. I better take it in order. We'll take this theory, and before we go to the next one, some definitions. The difference between ionization and dissociation. Ionization is a process whereby a neutral thing becomes a positive or a negative ion. And in the case of acid-base theory, it's a molecular compound. That is, our generic acid, we write it like that. So that shows the proton, and this is anything else. Right? This is a molecular compound, and as a consequence, it has no ions that are identified in the compound. Now, when you put it in water, this dissociates into an ion, a positive ion and a negative ion. That's ionization. So in the process, we had to transfer an electron from here to here. Okay, to make that positive and this negative. That's characteristic of Arrhenius acids. Okay, like the one before. Just does that. For bases, though, Arrhenius bases already have the hydroxyls, but they can be identified as an ionic compound. That is, they already have positive ions, negative ions in the compound itself. So our other example of an ionic compound was table salt. Right? So it would be sodium and chlorine together like that. Bases are just another type of ionic compound, and when you put it in solution, it just dissociates. Right? So there's no formation of an ion. The ion's already there. That's why we call it dissociation. It just splits. Whereas to form ions here, you have to transfer an electron. and that process is ionization. I know it's a subtle distinction, but focus on the acids are molecular compounds that ionize, and bases are ionic compounds that simply split, dissociate. And this came straight out of your book. It just illustrates what I showed you here. Okay, so which of the following describes an Arrhenius acid and base? Well, the acid has a proton in it that ionizes, and a base has a hydroxide in it that dissociates. Now let's see if they're going to let me go to the next one. Yes. Okay, so the problem was that Arrhenius definitions did not cover all the bases, particularly for, no pun intended, cover all the bases for bases. For instance, if you start off with ammonia gas and you dissolve it in water, right, so now it's aqueous. We just bubble it through water, and you form this, you get a basic solution. Right? So you're going to end up with hydroxyls over here. Right? So how does it do that? Well, this is what we think happens. Water is the dominant species, so it's likely that it reacts with water. And when it does, it picks up a proton from water. It ionizes and transfers that proton to the ammonia to make the ammonium ion. So what's left over is the hydroxide, because this produces that and that. Right? 2 hydrogens, 1 oxygen. So if the proton comes over here, it leaves behind a negative charge, and there's your hydroxyl. Okay? So what Bronsted and Lowry independently proposed was a new definition for acids and bases. And theirs is the dominant theory now for aqueous solutions. It focuses on the proton, and you just set the hydroxide aside for now. And an acid is a proton donor, a base is a proton acceptor. Right? So that covers ammonia, because what happens? Well, with ammonia, it accepts a proton from water. That makes it a base. Okay. So, more definitions. So if we have an acid, well, it's already there. So if we have an acid here, hydrochloric acid, and it reacts with water, then this is the proton donor. It's an acid. The water becomes the base. It's a proton acceptor. So the base accepts a proton, ends up here. The acid donates a proton, ends up there. Okay? So what do you have after the reaction? Now you have a proton acceptor. In the fluoride ion, it can accept a proton, which makes it a base. But it's derived from this acid, so we call it a conjugate base, because it's a product of the reaction. And the conjugate acid is formed from this base to produce this ion, which is the acid. It can now donate a proton. And this has a name. It's the hydronium ion. Okay? Notice something else about this. This conjugate acid is formed from that base by the addition of 1 proton only. We don't do multiple protons. When you have an acid-base reaction, you can transfer more than one proton, but it happens in steps, one at a time. So we only transfer one proton at a time. If we want to transfer another proton, say we have sulfuric acid. That has 2 protons available. In that case, we would transfer 1 proton right? So this would be the acid, this would be the base, the acceptor, this would be the conjugate base, that acid, and this would be the conjugate acid of the base. But we only transfer 1 proton. So when you do your homework or you see a question on a test, pick out the conjugate, the acid-base conjugate pair. This would be the acid, this would be its conjugate base, and it can only be the conjugate base if it has transferred just 1 proton. If we said something like this, right, acid, that's not a conjugate acid-base pair because we transferred 2 protons. Okay? Of course, the other thing, sometimes we give trick questions. If we say this, and then we say this, that's not a conjugate acid-base pair either, right? Because that couldn't come from this at all. So that's why I call it a trick question. Okay. So those are some definitions that you need to deal with. The hydronium ion is where the proton ends up in aqueous solution, more often than not. And it's characteristic of protons that they never float around by themselves. In reality, you never have that in aqueous solutions. They're always attached to something. Okay. However, you will see this used independently as a convenience. For instance, if we were to write that equation without the water, right, we could do calculations with that, right? Concentration of this, that, and that, and do an equilibrium situation. But that's not reality. That's convenience, because that never exists by itself. Okay. Yeah, they just don't make these things black enough. They're made for these little erasers.
Yeah.
So, conjugate acid-base pair here. Well, there's the acid because it's the proton donor. So its conjugate base would be missing 1 proton here. So that's an acid-base pair. Acid, conjugate acid-base pair. Oops. Go back, go back. There we go. Now let's look at water. In solution, not in solution, pure water. There's nothing in there but H2O. Will react with another water molecule. Actually, it's in equilibrium. It goes forwards and backwards. One of these becomes the acid, one of these becomes the base. That's what we mean by amphiprotic or amphoteric. You'll see it both ways. Amphi just means both. It can be an acid or it can be a base. So if this is the acid, that's the one that donates the proton. This is the base, that's the one that accepts the proton. So if this is the acid, it's going to end up as, let's take the base first. If it accepts a proton, it becomes the conjugate acid, right, of this base. And then if we take this one, it lost a proton, so that's the conjugate base. Now we can accept a proton, and this one can donate a proton. Okay, that's what water does. Most of it stays over here. The equilibrium is very, very small number, which means there's just a little bit of this. There's a whole lot of that. Okay, but the reaction does occur, and it's going to go. I think stream of consciousness. I want to stick with this for right now. There's probably a slide for it, but I want to take this and run with it. Remember when we wrote our equilibrium expression in the last chapter for a reaction? Remember that, the K value? Okay. Everybody remembers that? So for this expression, we would have the concentration of that one times the concentration of this one. That needs to be bigger than that. Right? Right? Products divided by reactants. Right? But if we combine these two, it would have a coefficient of 2, right? But these are pure liquids, aren't they? Remember what we said about pure liquids and solids? They don't count. Okay. So the actual expression for this, and we give it a special K, we call it KW for water. And then it's this expression only. There you go. For that reaction, this is the equilibrium expression. And the value of that product is always 10 to the minus 14. So like I said, it's very small, which means there's very little of this produced. There's some, but very little of it. And notice also that in pure water, if you've got this, then it comes from equal amounts of these two, right? Because they're 1-to-1 ratio, right? So equal amounts are produced in pure water. So what two numbers multiplied by each other would give you that? 10 to the minus 7, 10 to the minus 7. And by the way, this is molarity. Okay? So in pure water, you have this much hydronium, this much hydroxyl, and they're equal. This is a neutral situation. It's not acidic, it's not basic. And no matter what you do to the water, whatever you put in it, acid, base, doesn't matter, this expression always has to be obeyed. So if we add acid to the water, this one increases, that one has to go down. Okay? So it'd be something like saying if we add acid, we'd say increase this one to minus 6, which is bigger than minus 7, right? And then this one would have to be minus 8 to give us 10 to the minus 14. Okay, we'll come back to that in a minute. Okay, monoprotic, diprotic, triprotic. This just tells you how many protons are available from an acid. Monoprotic, example, hydrochloric acid. It's only got one proton. Diprotic, sulfuric acid, it's got 2 protons. Triprotic, phosphoric acid, it has 3 protons available. Okay? And sometimes we lump anything there or bigger. There are some quadriprotic, but sometimes we just call these polyprotic. Just lump them all together. Monoprotic versus polyprotic. Okay. Now, what do we mean by strong acids? The temptation is to assume that a strong acid is automatically dangerous. In chemical terms, strong acid doesn't necessarily mean dangerous. Strong acid means that the equilibrium position for the acid when it reacts with water is way over here. In fact, for all of these, well, the first 3, hydrochloric, sulfuric, not so much phosphoric, but hydrochloric and sulfuric, when they dissociate their first proton, they're 100% this side. In other words, if you know the concentration of, say you make a solution of hydrochloric acid and the concentration is 0.1 molar. As a strong acid, you know that this concentration is also 1 molar because it's 100% conversion from that side to this side. Okay? But the danger comes in how much of that is there. If this is very high concentration, like say if we change that to 10 molar, that would be dangerous. But 0.1 molar would not. You know, you'd be able to find out where all the cuts were on your hand. Right? It would stimulate those nerves, but it wouldn't eat through your skin. Whereas this one would eat through your skin. But it's still a strong acid either way, simply because it's 100% dissociation. Okay, see the difference? Here are examples. All of the, well, not HF, but the halogens from chlorine, bromine, iodine, those are all strong acids. HF takes a little explaining. We did talk about electronegativity, didn't we? Did we not? The tendency for an element to draw electrons to itself. Maybe we didn't. Okay. The most electronegative element in the periodic table is fluorine. It draws electrons the strongest of all the elements. As a consequence, it forms a very strong bond with hydrogen, HF, hydrofluoric acid. And it dissociates, actually ionizes. It ionizes to hydrogen and fluorine very weakly because it strongly attracts that hydrogen and its electron. So that's why HF is a weak acid, whereas hydrochloric acid, hydrobromic, hydriodic, those are all strong acids, 100% dissociation. Nitric acid is another example. Chloric acid, perchloric acid, sulfuric. Perchloric is extremely dangerous if it's sufficiently concentrated. And I used to use it in a concentrated form. It's very effective at digesting plant material. It just completely destroys all the organic matter and leaves you nothing but ash. But you have to be careful with it. Did I tell you this one before? You put a chunk of butter in a beaker and cover it with perchloric acid. Put it on your hot plate, turn the hot plate on high, then pull the sash down on your fume hood and evacuate the building because it will blow. That's how dangerous it is. The other point here, I know I made it before, but I'm going to emphasize it again. For polyprotic acids, the only strong proton in that acid is the first one. So the strong dissociation of sulfuric acid is the first dissociation. That one's strong. If we take this one and do the next reaction, then you get sulfate plus another hydronium. This one's weak because most of it is over here. Okay? It dissociates this one completely, produces that, and only some of that becomes this. So most of it is right there. The only way you have access to this other proton is by titrating it with a strong base. That is, put something in there with it that has a very strong attraction for protons, and then it'll strip all those protons away from it. That's how you get access to the second proton. But dissolved in pure water, that's the major component because that's strong and this is weak. And that's characteristic of all the polyprotics. If they're classified as strong acids, it's only the first proton that's strong. A weak acid, actually, this should be a double barbed arrow. So it's one going this way and one going that way because it's an equilibrium situation. Most of it is over here in the unionized form. And a little bit is over here. This is the author's idea of an explanation for that. Strong acids, all of this makes all of that. Weak acids, only a little bit of this makes some of that. Most of it is still here. Okay, strong bases, a similar concept, only now we're dissociating, we're not ionizing. So these bases are all strong and all completely soluble. That is, 100% of it goes into solution. If you start with a solid, like you start with grandma's lye, sodium hydroxide, it'll go into solution, every bit of it. And when it does, it will completely dissociate into sodium ions and hydroxyl ions. That's characteristic of all the group 1 hydroxides. The group 2 hydroxides, the ones next door, right? Well, at least the calcium, strontium, and barium hydroxides, they have limited solubility. But whatever goes into solution, whatever part of this does actually dissolve in water, dissociates 100%. Okay, I know that's another fine distinction, but you will have, if you put this solid in water, most of it will just sink to the bottom, sit there. But there's some of it in solution, and the part that actually goes into solution is dissociated into calcium ions and hydroxide ions, 100%. Okay, that makes them strong, although they have limited solubility. Okay, so which of the following equations would be the correct representation of a strong acid when placed in water? Okay, they each look like they have the same products, so we concentrate on the arrows. Strong acids would be mostly this direction. Oops, like that. Okay, when we describe the equilibrium constant for an acid, the proper way, of course, is to react it with water, produce the hydronium and the conjugate base, and then construct the equilibrium expression as hydronium conjugate base divided by acid. Okay. Now that's a valid expression for equilibrium expression for a weak acid. A strong acid would have no value. This expression has no value for strong acids because you're producing all this over here, and this is approaching 0. So what do you get when you divide the numerator by 0? Infinity, right? Divide anything by 0, you get infinity. So this expression has no value for strong acids, at least the first proton. But weak acids, yes, because you produce some of this, most of it's over here. So this is going to be big, this is going to be small, and the K value is going to be small. Something quite less than 1. For instance, acetic acid. Okay, reacted with water, and you get hydronium plus acetate. Okay, so there's your conjugate base from a weak acid. There's your base, water acting as a base, making the hydronium, which is your conjugate acid. The expression here, Ka, would be this one times this one divided by this one. Okay, and the value for that is 1.8 times 10 to the minus 5th. So it's a very, very small number, right? 100,000, 100,000, or 1.8. 100 times hundreds, thousand. So most of it is here, and just a little bit's there. So vinegar is a weak acid. That's vinegar. Well, actually, 5%. Mass volume is vinegar. Okay. So this is the equilibrium expression, and as long as we don't change the temperature, that value is a constant. Right? So if you do anything to one of these, it changes the other one to make that one constant. Percent ionization is a different concept. And it simply means that we take this value and divide it by this value at equilibrium and times 100. So we leave this part out. We just want to know how much of it dissociates when we put it in solution, right? So the percent dissociation for our acid is not a constant because we left this part out. You have to include that part for it to be constant. So this part can vary depending on how much of it you put in solution. This is true. The strength of the acid increases as you increase percent ionization. So the stronger the acid, the more of this you're going to have from that. That is true. If we had a value here of 10 to the minus fourth for a different acid, the percent ionization would go up. And the, well, this doesn't have anything to do with percent ionization, but the strength of the acid does increase as we increase this value, because that means more of this is being produced. So they are related. And that's all we're going to say about that. So you can, if you're given, what's the equilibrium concentration of this, equilibrium concentration of that, can you calculate percent dissociation? Yes. Just use the formula. Okay. We can do an equilibrium expression for base too. So how do we write that? Well, if we have a base of some kind, we'll use the generic first, and then I'll give you an example. So we take the base, react it with water, and the base, of course, has to be a proton acceptor. So now the conjugate acid of the base has this extra proton. And this was the proton donor for, so in this case, water is the acid. And now this is the conjugate base of that acid. Okay. Oh, we did one already. If this is ammonia, that's a proton acceptor, then we end up with that. Okay. And if we substitute these in that expression, then this is there, and this is there. So we use these two instead of those. Okay? But when you do that, characteristic of the Kb value is that in the numerator, you will have hydroxyl instead of hydronium. That's a giveaway. So what does salt mean to a chemist? All right, to a cook, sodium chloride is salt. Or potassium chloride is light salt. But to a chemist, a salt is the product of an acid-base reaction. When you put an acid together with a base, and we're going to use Arrhenius base here, something that has hydroxyl already. Then what you get is a double replacement reaction. In other words, you swap these two. Swap the B for the H. So that becomes, the B is the cation, the A is anion, and then this hydrogen is associated with the hydroxyl, and you get water. Okay? So here's our acid. Here's our base. This is our salt. The salt is the result of an acid-base reaction where you take the cation and anion from the acid base, put them together, and then what you have left over is water. Okay? Okay. Example, hydrochloric acid, potassium hydroxide makes light salt and water. Sulfuric acid, in this case, we're going to extract both of those protons and put them over here along with two hydroxyls that go over there. Right. So like I said before, if you want access to both of these protons, all you need is a base to react it with. And then you can get both of those protons. So now we're not talking about just putting sulfuric acid in water and saying which protons dissociate, ionize, excuse me, use the right terminology. In this case, an acid-base reaction will give us access to both those protons. And now both of them are over here, and we produce this salt. That's called a neutralization reaction. If we allow for the stoichiometry for 1 mole of this for every 2 moles of that, then we get exact reaction with the two and neutralizes solution. So this is a solution as we add it together with this solution. This one's acidic, this one's basic. When you put them together in the right proportions, you get a salt dissolved in water, neutral solution. In this case, because that's a strong base and that's a strong acid. So the consequence is a neutral solution. Okay. Okay. So this is what's actually happening. Let me back up. This is a summary of what's happening, but actually what happens is this sulfuric acid forms hydronium ions, right? So as the hydroniums are required, sulfuric acid forms more of them. And then the base dissociates and produces the hydroxyls. Then those react together to give us 2 waters. This is what's known as the net ionic equation. And for a neutralization reaction, this is always the equation that operates. Acid, base, water. That's it. So you can change the acid, you can change the base, and you still get this. That's what they're trying to illustrate. Yeah, that's a hydroxide. I was looking at all these lone pairs. That's good. Any questions? How we doing on time? 10 o'clock. Okay, good. I want to give us as much time as possible in the lab, so we won't be rushed. So we always form water and a salt when we react acid with a base. Okay, so this is the slide that I was referring to earlier when I was showing you the equilibrium expression for water reacting with itself. Okay, so that's what it does. That just one of them transfers a proton to the other one, and you get a hydronium and the hydroxide. And there's your K expression, equilibrium expression for water at 24 degrees. Okay, if we deviate from 24 degrees, then that changes slightly. But for all intents and purposes, you know, if you're not too far afield from 24, then this value will be relatively constant. And like I said before, no matter what you do to water, what you add to it, this expression has to be obeyed. Of course, if you add sodium chloride, it has no effect. If you add acid, it's going to bump this one up, and that one's got to go down. If you add base, this one goes up. That one has to go down because it's constant. And this is just expressing the same thing that I said in words. If you add acid, then you increase the numbers here, right? It goes from -14. So down the scale is an increase in hydronium. Then the other side has to go up, which makes it smaller. So that the scales are inverted. We normally think larger is up here, but in this case, larger is down here. And then same thing, if you add base, it just flips it. So you get less hydronium and more hydroxide in order to keep that expression constant at 10 to the -14. Okay, if you have equal amounts in pure water, that would be 10 to the -7 equals 10 to the -7. That's a neutral solution. If you add acid, acidic solution means this is bigger and that's smaller. Basic solution, this is smaller and that's bigger. It's really simple. So let's take this as an exercise and see if we can make sense of it. So we have two different solutions. We want to determine whether it's neutral, acidic, or basic for each one. So what we have to do is find out what's the relative amount of each one of these, which one's bigger, to tell you whether it's acidic or basic. So there's our expression. We have this concentration for the base, right? So we can find out what this concentration is. Just plug it in here, solve for the unknown, right? So there we've solved for this one. That means this one comes over here into the denominator. There it is, that value. Then our value here for hydronium is 10 to the -10. So 10 to the -10 is less than, is greater than, excuse me, greater than 10 to the minus, no, excuse me, it was greater than this, but it's less than this one. So that means it should be basic, right? The hydroniums are less than the hydroxyls. It should be a basic solution. And that, stabbing me in the back again, this should be a less than sign. So since this is less than that, we have a basic solution. There. This one, we don't have to do a calculation. It's already for us. We know what the hydrogen ion concentration is. Oh, we're comparing it to the neutral. All right, so if this is neutral, and that's less value than the neutral, it has to be basic, because this is the hydronium concentration. Right. Either way, this is less than that. It's also less than that. It has to be basic. This is greater than that by quite a bit. Okay, so a question just occurred to me. Strong acid versus weak acid. Is it possible for the weak acid to have a greater hydrogen ion concentration? Is it possible for the weak acid to have a greater hydrogen ion concentration than the strong acid? Yes. It all depends on how much you put in solution. If you put in solution here, say 0.01 molar, right? So that's going to dissociate to that concentration for here. But what if we make acetic acid? You can get acetic acid, C1002. You can get acetic acid 100%. It's called glacial acetic acid. So if we compare this one to that one, that's 100%, and it dissociates at 10 to the minus fifth. And this might have to be a little smaller. Maybe. Then the hydrogen ion concentration here will be greater than the hydrogen ion concentration here. Even though this is a weak acid, it does have a higher hydrogen ion concentration, I should say, to be consistent. Okay? That just emphasizes the point that we made about strong acids. Strong acids just mean 100% dissociation. It doesn't say anything about whether it's hazardous. This would be hazardous. You don't want to stick your finger in there. But this, I mean, that would be less than stomach acid. Stomach acid is 0.1, about 0.1 molar hydrochloric acid. Depending on what you're eating. You know, if you're eating Italian, it would probably be higher concentration. It's called the tomatoes. Okay. So, up to this point, we've been dealing with molarity. What's the molar concentration of these ions? Hydronium ions, hydroxyl ions, any of their spectator ions that form the salts. But the Danish chemist Sorensen in 1909 proposed a simpler way to express hydrogen ion concentration. He called it pH. Right? Everybody's heard of pH, right? It's simply a mathematical expression. And here, I know this says hydronium, but very often you'll see it this way, right? Even though we know that protons don't exist alone, it still expresses the same value. So if you know the hydrogen ion concentration, then you can calculate the pH, right? Now this is the common log. That means the base is 10. Everybody remember how to do logs? Right? The definition of a log. So if you have the log, in this case, base 10, some value is equal to y, what does that mean? That means that this is the result of that to that power, right? So if we resolve that into that definition, we say this to the y power equals x. Okay. And for purposes of calculations on your calculator, you would see an log button to calculate the log of a number. But if you have this number and you want to find out what that number was, which would be the hydrogen ion concentration, you would look for the button that says 10 to the x on most calculators. Right, so just plug in. Of course, you have to use the negative value. We'll do an example. That'll make more sense. Go. So there's our definition. And there are some things about the pH that you need to grab hold of. And the best way to do that is to illustrate what pH means in terms of hydrogen ion concentration. So if this is neutral, the hydrogen ion concentration, or the hydronium concentration, is 10 to the minus 7 in water, right? So if it's more acidic, it would need to be, this is the acid end, this is the base end. It would need to be a higher concentration of hydrogen ions, right? So let's go up in steps of orders of magnitude. 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, And you can go up to 10 to the minus 1. Okay? More concentrated makes acid. Hydrogen ions, hydronium ions. Less concentrated, so we do 10 to the minus 8, 10 to the minus 7, 10 to the minus 6, 10 to the minus 5, all the way down to 10 to the minus, let's say 10. Okay? So that's actual concentrations of hydronium ions or hydrogen ions. We're using them synonymously. Same thing. Now, what if we do the log transformation that Sorensen proposed? Right? For example, let's take the middle of the road. So negative log to base 10 of 10 to the minus 7. What would that be? Well, the log of this number is the power of 10. Right? So the log of that number is minus 7. You plug it into your calculator and it'll tell you that's minus 7. But Sorensen said, I don't want to deal with negative numbers either. So he just stuck a negative out here. So that makes it positive. So in this case, pH is equal to 7. So this one is pH down here is 7. So if we do 10 to the minus 6, this one will be 6, 5, 4, all the way down to 1. So the point is, as the hydrogen ion concentration increases, the pH decreases. A smaller number for pH means more acid. And then we can go backwards. 8. That's 9. Excuse me. 9, 10, 11, 12, 7, 8, 9. So this would be 9, 10, 11, 12. So as the pH gets bigger, the hydrogen ion concentration decreases. What would the OH concentration be? Remember, they have to multiply to be 10 to the minus 14th, right? So the OH concentration here would be 10 to the minus 13. And this would be 10 to the minus 7. And this would be 10 to the minus 2. There we go. Okay? So, this is purely a mathematical expression. You can stick anything in here you want to and get a p-value for it. So we can do the same thing for hydroxyls too. Negative log of hydroxyls. Okay? So if we did that for, let's say this one, 10 to the minus 2. Negative log 10 to the minus 2 equals 2. So the POH here is 2. And here is 7. And here is 13. Okay? Notice something else. If you add the pH and the POH together, what do you get? 14. 7 plus 7, 14. 1 plus 13, 14. The pH and the POH always add up to 14. Okay? So, I need some room here. Let's see. Let's erase this one. So why is that? The reason is that we can also write Kw. Remember Kw for the expression is, let's do it this way first. What's the Kw? There. That's the Kw. Now, what if we do a P transformation for that entire equation? Just say negative log of the whole thing. That means negative log of this equals negative log of that. And what happens to products when you take the log of them? In other words, if we say log of x times y, what's that equal to? That's log of x plus the log of y. That's the definition of logs. So in that case, the negative log of this one is plus the negative log of that. Okay? And then the negative log of this one is what? Negative log of 10 to the minus 14. Now this one becomes pKw. Right? This one becomes pH. This one becomes pOH. And this one becomes 14. Okay? So the pKw for water is 14. And whenever you add these together, they always have to be 14, just like we showed here. So if you know the pH of your solution, right, say it's 2. This one has to be 12 to make 14. If the test question says, what's the hydroxyl concentration, hydroxyl ion concentration for this solution, if the pH is 2? Simplest way is use this expression. If you know 2, then you know 12 here, then the negative log of the hydroxyl is equal to 12. Then you say, need more space. That's probably dropped off forward, so put it down here. Then you say, the negative log of the hydroxyls is 12. Resolve that expression. Well, if that's base 10, then we take that negative and put it over here. Then we have the log expression and the hydroxyl ion concentration is actually 10 to the negative 12 power. So now the hydroxyl ion concentration is that. So that's easier than going through this expression to find out what it is, I think. Okay. Let's see, we ought to be getting 30 minutes close, huh? What's next? Okay. What happens when you dissolve salt in water? we know how to make salts. But what happens to them when you put them in water? That's the next question. If you actually start with a salt and you put it in pure water. Okay. We just did a problem like that. Oh, okay. So before we jump into that other topic, let's finish this one. If the pH of a solution is 5.85, what's the concentration of hydronium ions? If you know the pH is this, then find the hydronium concentration. You just need 10 to the minus 5.85. Plug that in your calculator. That's 1.4 times 10 to the minus 6. Okay. Before calculators, we had to look these things up in tables. It was a pain. The first calculator I bought would just do basic stuff. It would do multiply, divide, add, subtract, logs, and powers. That's it. Nothing else. It's about regular size, but it was that thick. And it weighed about a pound. And it had a pouch. You hook it on your belt and walk around and it pulled your belt down all day. Come a long way. Before that, I used to live in Atlanta, and we had Georgia Tech. You've heard of Georgia Tech. Ramblin' Wreck from Georgia Tech. They were all engineers. So I had to do calculations. Before calculators, there was the slide rule. You've heard of a slide rule? It kind of looks like a ruler, only it's got a slider in the middle of it that goes backwards and forwards. A long piece that's the same length as the slide rule, slides back and forth. Plus, there's a little sight glass that slides back also, back and forth. And you use those things to do your calculations. And they work great. You know, some of them are like that. I've got one made out of bamboo about that long. And these engineers would have to have things with lots of functions on them, and they'd be like that. So it was a sign of stature to have your slide rule hooked on your belt, and your pouch wasn't that long, but your pouch was this long. That means you're like a senior. Okay, so these are some relative pHs for different substances, right? So fruits be in this range, they're acidic mostly. Peaches, pears. I'm surprised tomatoes are a higher pH than, well, these citrus fruits, you can understand that. Carrots, peas, butter even is slightly acidic. Has anybody had anatomy and physiology here? So you know what the ideal physiological pH range of your blood is, right? Do you remember?
pH semester, so I don't even know.
I think, if I remember correctly, it's 7 point, slightly basic. Wait a minute. Yes. 7.35 to 7.45, I believe. Very narrow. Okay. We're going to talk about that in a second. It's called buffering. If you get outside that range, blood goes acidic or basic, and you start to feel it in a hurry. And diabetics, they can go into a state called ketoacidosis, and your pH, the blood pH drops way down, and it's dangerous. In fact, if it drops far enough, that means your blood sugar is going way up too. They happen together. pH goes down, blood sugar goes way up, like 500, 600, 700, then you better get to the hospital. And if you have somebody in the family that smells your breath, they're going to smell acetone on your breath. You know what acetone smells like?
Like fingernail
Fingernail polish remover. Yeah. Yeah. If you smell acetone on a family member's breath, get them to the hospital quick. Okay, so pH, there's the expression for pH. Let's see. Oh, we did this already. There you go. So if you take the negative log of each one of these, just like I did on the board, pKw is always equal to 14. So here's the Ka, which is the acid dissociation constant. Actually, it should be acid ionization constant. For HF is 6.8 times 10 to the minus 4. Right? So it's a weak acid. And the pK for that is 3.17. Right? It's still an acid, because anything less than 7 is going to be acidic. Anything greater than 7 will be basic. Right? So there you go. It's acidic. Now salts. What happens to salts when we put them in water? The best way to think about this is to consider, where did each of the ions, the cation and the anion from the salt, where did they come from? You know, what would their acid source be for the anion? What would the base source be for the cation? And then look at how those behave in water. Okay? So if we have sodium chloride, right, where did that originate from? If this is a salt, right? So the acid-base neutralization reaction would be sodium hydroxide plus hydrochloric acid, right? And that would produce this plus water. Okay? So this is a strong base. This is a strong acid. So when you neutralize them, you end up with this. Dissolve that back in water, you get a neutral solution. Why? Because what happens to this when you put it in water? It makes that plus this, and this one makes this plus that. Okay? Now, what is the tendency? This is a reverse reaction too. Go backwards. What is the tendency for this one to go backwards? Almost zero. It's here, stays there. So if you put this in solution and makes this ion, is it going to react with anything in aqueous solution? No, it's just going to sit there, do nothing. Same for this one. Since it's strong, it wants to be here, right? This has no attraction for the proton in a water molecule. So that's why it's neutral. They do not react. Neither of these will react with water to produce the original acid and base. So strong, a salt that's formed from strong acid, strong base is neutral solution. That's the easy one. Next one. Come on. Enough of the animation. Here we go. If a salt is formed from a strong acid and a weak base, right, like this one, ammonium chloride. Right. So where did they come from? Well, this is the reaction that produced that salt, the weak base and strong acid. So why do we call that a weak base? Well, what's it going to do? Well, in solution, I'm going to simplify this a little bit. We're going to take the water out of it. So if this is weak, it stays over here. It doesn't produce a lot of that. So it's a very small amount of this. So we take this and put that in solution. Is it going to, well, let's see. Yeah. If we put this in solution, part of that salt, and let it react with water, what's it going to do? Well, if the tendency is to be way over here, it wants to be there. So how does it get there from here? It picks up a hydroxide. Right? And what does that leave? That leaves a proton. Right? Takes a hydroxide from this, leaves a proton. So what's the end result of putting that one in solution? Acidic. But the chloride is just like the sodium chloride. It doesn't react with water. So it has no influence on the pH. This is where the pH comes from. It makes an acidic solution. If you have a weak base and a strong acid, you get an acidic solution. Okay, that's why it happens. Now here's the rule of thumb that I use. If you have weak, strong, this comes from a strong acid, your solution is acidic. Right? Okay. That's my rule of thumb, but this is why. Okay. So if we flip it around and say strong base, weak acid. So here we have sodium acetate. Right? So this is from a strong base and a weak acid. So my rule of thumb should say what? Basic. From a strong base and a weak acid. Now here's why. The sodium doesn't react with water. Right? We showed that with sodium chloride already. But this one does. If this is from a weak acid, its preferred form is this one. It wants to be here. So how does it get there? It takes a proton from water, right? And what's left over? Hydroxyls. That's your base. So the reason it's basic is due to the weak acid, not the strong base. But my rule of thumb works as strong base, weak acid makes basic solution. So the strong one determines this by rule of thumb, but the weak acid determines this by chemistry. Now, what's the other possibility? Where they're both weak, right? So if they're both weak, you can't tell, not easily. If they're both weak, you need to know which ones, if they're exactly equal in their dissociation constants, then you'll have a neutral solution. But if one is a larger number in its dissociation constant, it will win. Okay. So we're not going to go into that depth because this is an introductory course. general chemistry, I get to torture my students with actually calculating which one's which. But we're not going to do that. Just know that if you have weak acid, weak base origins for your salt, then the pH, or whether it's acidic or basic, is dependent on the actual dissociation constant for each one. So we can't tell yet, not easily. These, yeah, we can tell. All three of those, we know exactly what they're going to be. Okay, buffers. I guess is the last point. What is a buffer? Okay, there's buffers. Oh, we're going to talk a little bit about electrolytes too. That's all right. Buffers. What is a buffer? Well, in common culture, buffers used to describe a whole lots of things. But in chemistry, a buffer is specifically related to acids and bases. And what it means is, if you have a solution that is defined as a buffer, if you add acid or you add base, the pH is not constant, but the pH changes very little. Okay, so it's said to be buffered at a certain pH. In other words, it's stable near that pH if you add either acid or base. Okay, it's not constant. There is some slight change, but for instance, with your blood, if the blood's buffered at that pH range, then if you inject acid into your system or base into your system, then it will compensate. It will hold it near that pH range until you exceed its capacity. You know, then you're in trouble. But we're talking about chemistry here, and pure chemistry, once you establish the buffer, you don't do anything more to it. Then as you add acid or base, it will shift a little bit, a little bit, a little bit until you exceed its capacity, and then it'll go, just, you know, it's gone. But for living systems, the buffering is active. In other words, your system is constantly adjusting your system for homeostasis. That is, it changes things to maintain that buffer pH where it is, no matter what you do to it. So it's a little more robust than pure chemical systems. Do you remember the primary buffer in your blood? The buffering system? Carbonate system. Remember that? Maybe not.
Did we talk about it in here? Or?
No. Anatomy and physiology.
Yeah. I didn't really retain the most info from anatomy.
And it could have been a while ago.
Because we talked about like pH and all that like at the beginning of last semester. I remember because we did like a lab and he had gave us like these little pH strips. So we like tested a bunch of different stuff. But that was like one of the first labs we did.
Okay. Okay, so that's a buffer. Every buffer contains two chemical species. Since it has to maintain pH whether you add acid or base, then one of those species reacts with added acid and keeps it from influencing the pH. It takes those protons or those hydroniums and puts them someplace else. It reacts with them. It removes them from solution. If you add base, another different species reacts with that base and effectively neutralizes its effect too. Okay? So you got to have both. Okay. Let's see. Most buffers, not all, but most, are produced using a weak acid. So the weak acid, reacting with water, produces the hydronium, right, which is the conjugate acid of the base, and the strong conjugate base of the weak acid. That's another concept. If you have a weak acid, it yields a strong conjugate base. If you have a strong acid, it yields a weak conjugate base. Now, we've talked about the difference between strong and weak acids. Right? A strong acid just completely ionizes. It makes hydronium ions and the anion. But we didn't talk so much about the difference between strong acid, strong base, and weak base. A weak base, since a base has to be a proton acceptor, if it's a weak base, it doesn't want a proton, right? It's happy right where it is. But if it's a strong conjugate base from a weak acid, which would be what? For instance, the acetate ion, right? It wants a proton, right? Because it comes from a weak acid. It wants that proton so it can go back and be an acid. So it has a very strong affinity for protons, right? So that's why weak acids make strong conjugate bases, strong acids make weak conjugate bases. So what happens? Well, if we're going to have a weak acid making, let's use a real example. Let's say we make our buffer from acetic acid, right? And it makes this one and this one. Okay, now we have this solution where we've got mostly this, but a little bit of that. So what happens if we add acid, right? Add protons. What's it going to react with? It's going to react with the strong base. That's the strong base, right? It's going to make more of this. So what happened to this? It's gone. It has no influence on the pH anymore. It doesn't make it acidic, right? We just added acid to it, and it's gone. What if we had base, though? What does the base react with? I have to say something else first. If the K value for this is 10 to the minus 14th, what does that mean? That means that was very little of this and a lot of that. So that means this is a strong base because it came from a weak acid. Right? Water is a weak acid. So that makes this a strong base. Okay, so if this is a strong base, what is it going to go for? It's going to go for this one right here. It's going to take the proton off of that and make this, and our base is consumed. Right? So this is the species that neutralizes acid. This is the species, this one neutralizes the base. Okay, so we have a buffer. Now, there's an ideal concentration at equilibrium of this one and this one that gives you the proper buffer zone. But this is the stoichiometry, the chemistry that created the buffer. Okay. Now, there are a couple of researchers that did some thinking on paper. And they said, all right, suppose we have a weak acid that's making these things. Weak acid makes strong base plus protons, and we're leaving the water out of this. You know, this is one of those times where you have to shift gears. So the expression for this weak acid equilibrium is that K value is this concentration times that concentration divided by this concentration. Okay, we know that already. But what they wanted was to quickly determine what's the pH of our solution if we know the concentrations. Right? So the pH would be related to this one right here. Okay? So that's where we're headed. We're going to solve it so we put the pH on one side and everything else on the other side. So first we solve for this one. So that means this one times this one divided by that one right here equals this one. Now that we've got hydrogen ions on one side, we can take the negative log of everything. So the negative log of this one equals the negative log of that one plus the negative log of this one, right? That's our log transformation. Okay? So this one is pH by definition. This one's pKa by definition. And we don't want to resolve this one yet because the ratio here, that's the important key to our buffer. So we're going to leave this one here, except we don't like that negative sign. So it's characteristic of log expressions. If you have the log of x over y, that's equal to the negative log of y over x. Okay? So we're just going to flip these, and that changes this to a positive sign. Okay? That's all I did. Just flip the numerator and denominator, and that changed the negative sign to a positive. This is the Henderson-Hasselbalch equation. So if you know the pKa of your weak acid, and you know the ratio of the strong base to its weak acid concentration, then you can calculate the pH of your solution. Okay? So what's the ideal? What's the pH of your solution? The ideal is where this one equals that one. And how do we get that? Well, we get rid of this term. So how do we get rid of that term? Well, the easiest way is to make this equal to 1, right? What power of 10 is 1, right? Because if this is 10, then the power of this equals 0. No, power of that, this is x. Power of that equals this, which is the total thing is 0. So if we want that to be 0, this has to be, no, we want this to be 1, excuse me. This has to be 0. So if this is equal to that one, say it's 1 and 1, or it could be 10 and 10, or half and half, it doesn't matter. As long as the ratio is equal to 1, then 10 to what power equals 1? 10 to the 0 power equals 1. Okay? So for this whole expression to be 0, these have to be equal. The conjugate base has to be equal to the concentration of its weak acid. Okay? So that gives you the ideal buffer zone when these two are equal. Now, if we were to do, I have my general chemistry class doing titration. So this is base, like sodium hydroxide, and you're titrating it against, let's stick to acetic acid, okay? Acetic acid. Right. This is your pH. So we start off at about in the neighborhood of 3. For nothing but your acid. And then we start adding base to it. So it jumps up quickly, but then it flattens out right here. Just like that. And then at a certain point, it goes like that. And then flattens out again. Okay? This point right in the middle there is called the equivalent point. That's when the amount of acid and the amount of base are exactly equal. Right? So when you're titrating and trying to find out the concentration of how much acid you've got in there, that's the point you aim for, this volume. But that's where acid is equal to base. Total acid equals total base. But what we want here is the weak acid right in here, which would be half that volume. 1/2 neutralization volume means that we've only neutralized half of it. So if we have this much to start with, then we converted half of it to here, which now makes them equal, doesn't it? Now they're equal. This is the buffer pH. Actually, the ideal buffer pH. The buffer could be anywhere in here. This is the buffer zone. Right there. Okay? Now, notice something else. If this term is 0, what is the pH equal to? pKa. So if we know the pH here, this is the pKa. Okay. That's the buffer zone right there. And that's where the conjugate acid, conjugate base is equal to what's left over of the weak acid. Okay, so what's the pH of a buffer solution that's, okay, so if we know it's 0.45 molar acetic acid and 0.85 molar acetate, so what we're doing is we're putting this acetic acid in there, and then we're putting in the acetate ion as sodium acetate. So we know how much we put in there. This is the HA part, right? And this is the A minus part of our expression. The A minus divided by the HA. So we know these two values. And we know the Ka for acetic acid. You just need to convert that to pKa, negative log of that value. There we go. So we know this concentration, we know that concentration, it's given to us. We know this value, we just need to convert it. Right? So if we do that, convert that, the pH of that solution will be 5.02. Okay, any questions? I know that's a lot to take in. What's an electrolyte? I had a friend of mine who's a professor of agronomy, and he was helping me with my PhD research. I was asking him, how do I describe this method that I'm using? He says, well, you know, the best way to describe it is say it's operationally defined, which means you develop a method and call it whatever you want to. So electrolyte is an operationally defined term, which means if your substance will dissolve in water and also conduct electricity, it's an electrolyte. So if we dissolve table sugar in water, will it conduct electricity? Nope. It'll dissolve in water, but it won't conduct electricity, so it's not an electrolyte. Why won't it conduct electricity? C12H22O11. That's sucrose. When you put it in water, it stays like that. Right? It doesn't make any ions. It has to make ions in order to conduct electricity. Right? So if we put sodium chloride in water, it produces ions. Conduct electricity, that's an electrolyte. Or if we put any kind of acid, it may only make a few ions, but it will still conduct electricity. It might be a weak electrolyte. So acetic acid here would be a weak electrolyte. Hydrochloric acid would be a strong electrolyte. There's a non-electrolyte. There's our sucrose. No light bulb. Strong electrolyte like hydrochloric acid or sodium chloride. Weak electrolyte like acetic acid or hydrofluoric acid or hydrocyanic acid. They're all weak. So they'll light a little bit, but not much. Those are weak electrolytes. So when your doctor gets a report back on your blood work, it has electrolytes in one group, and they're the ions, like how much sodium in your blood, how much chloride, how much potassium, calcium, magnesium, any other conductors, maybe some anions that are of importance. Those are all your electrolytes because they allow your blood to conduct electricity if necessary, or if tested. Okay. Now here's a term that is very useful if you're working with acids and bases and titrations where you neutralize them and you want to know exact values. This concept is very useful, but for most people who just go through the course and they just wanted to go to the next step, you'll never see it again. It's called the concept of equivalent. So what's an equivalent? Equivalence is related to the charge. So that, if it's 1 molar solution, is 1 molar equivalent. Or actually, if that's 1 molar, it's 1 equivalent per liter. Okay, because the equivalent is an absolute amount. What if we had this one, the sulfate ion? If that's also 1 molar, we have 2 equivalents per liter because we have 2 charges. Okay, that's all that means. milli equivalent is just 1,000th of an equivalent, 10 to the minus third equivalent. Oops. Oh, this is your blood, the plasma in your blood. And it's usually given in terms of milli equivalents per liter. And not always, but that's a common expression. Sometimes it's given in milligrams per deciliter. We'll do your homework problems and see if none of these crop up on your homework, then we won't worry about it. Okay. This is just dimensional analysis. If you have 180 milliliters of the sample, that is 5.3 milli equivalents per liter of calcium, then we have to, this is the key right here. 1 mole of calcium is equal to 2 equivalents. Then that gives you so many milligrams of calcium ions. Okay. So when do we use things like this? In titrations. So if we were to titrate hydrochloric acid against sodium hydroxide, right, we would get water, right, this one, and sodium chloride. That's balanced. So what's the relationship? Well, if we have 1 mole of this, it takes 1 mole of that, right? So it's 1 to 1. But if we were to say titrate sulfuric acid against sodium hydroxide, we need 2 of these. And then we have 2 waters plus there. So in this case, it would take 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. The reason is this one makes 1 equivalent right here. This one makes 2 equivalents. So it takes 2 of these to match that one. Okay? So this makes 2 equivalents. This makes 1 equivalent. So we have to say 2 times it. That's why the 2. Now, when they're completely neutralized, that point, I showed you that before on the graph, the equivalence point, that's where moles of acid equals moles of base. That's the equivalence point. But we don't always have access to a meter that will give us the pH. A pH meter will read off the pH continuously as we add base. Right? But we don't always have that, and that's very tedious. So I've done titrations where I have 100 samples. You don't want to do a pH curve on each one. It'd take forever. So you use an indicator, something that will change color when you get very close to the equivalence point. It won't be exactly on the equivalence point, but the error will be so small, it's insignificant, right? But it's a lot quicker. So we use that color indicator, and when we get to the point of color change, that's your end point. That's the difference between equivalence and end point. Whereas acid-base indicator, well, I thought it was going to say. It doesn't. Mill equivalents. Here we go. Come on. Well, that's the end point. When the color changes, that's the end point. And you choose your indicator so the color change occurs very close to the equivalence point. And you can, if you choose it correctly, you can ignore the, now we were going to do one of these titrations, but we ran out of time. It was our last lab. So today is the last lab because we don't have time to get the other one in. But it was going to be a titration using a burette. Okay. So let's see, what else do we have here? Okay. If you have, at the equivalence point, the moles of acid equals the moles of base. That's a stoichiometric problem. So if you have a molar concentration, which is what? Moles per liter, is equal to moles divided by volume, right? And if you want moles of one to equal moles of the other, solve for moles. N equals molarity times volume, right? So if you want this number of moles equal this number of moles, then this is equal to molarity of your acid times the volume of your acid, and this is molarity of the base times the volume of the base. Right? So if you set those equal to each other, and you know the volume that you start with for your acid, and you know its molarity, the concentration, then all you have to do is add enough base to where these are equal, and then you can solve for the unknown part for the base. That's only if it's 1 to 1. If it's here, then you need something different. And I'm not sure if there's an expression for that. You need the molarity in terms of equivalence. There's not a value like this for that. But as long as they're 1 to 1, you can use that expression. If they're, oh, I know what it is. Excuse me, I know exactly what it is. It's N. Normality. Okay. Normality takes into account equivalence. So if you know the equivalent concentration, so if sulfuric acid is 1 molar, actually, let's make it half molar. If it's 0.5 molar sulfuric acid, what's its equivalent concentration or normality? It's 1 molar, 1 normal. Because for each mole of this, you have 2 hydrogens, right? So 1 normal. So if you know the normality, then you can use this expression. Is that the end? Yeah, that's the end of it. Okay. I ran longer than I expected. So we're going to the lab and do our next lab. Take a 5-minute break.
So since I cannot write, you mind if I like hang around? And
Oh, yeah.
Make sure someone's data.
Observe. Oh yeah. So let's stop the recording.